Let's begin with a fun activity. Identify the movies whose pictures will next appear on screen. Pause the video and try to identify as many movies in shortest possible time. Done? Here are the answers. Now let's go to the next part of the puzzle, which is more interesting. There is one common thing about all these movies. What is it? Go back in the video if you want and try to find out. The answer is time. Where time travel has been widely used topic in sci-fi or fiction movies, it is also a very important part of special relativity. So what is time? Now we know some common phrases about time like time is illusion or time is money, but I'm not talking about that time. What can be the physical definition of time? One might suggest that time is a unit of measurement for any duration. Correct. But that is not a definition, it's just saying its use. Someone may also say that time is something which is unidirectional. That is, it only flows in one direction, as we can't go back in time. Correct. But again, that is a property of time and not as such a definition. If you are a fan of sci-fi movies, then you might suggest that time is fourth dimension. That is, just like three space dimensions of length, breadth, and height, time is also a dimension. Very well. This is the nearest to the statement that I am about to make to define time. Time is an instance of happening an event. Now, before we elaborate on this, let's ask another related question. What is an event? An event is defined as something that occurs at specific point in space and at specific instant. For example, you reading at library at 10 a.m. is an event. Similarly, you watching TV in your living room at 7 p.m. is another event. So, we can say that time t, just like three space coordinates x, y, z, is another coordinate required to specify an event. In that case, we can also say time is a dimension. Now, is just a set of four coordinates x, y, z and t sufficient to specify an event? Or do we need something else too? No, only the coordinates are not enough. We must also decide with respect to what these coordinates are specified. This is essential because often things look differently from different perspectives. We will call this reference point of view a frame of reference. Let's understand this concept with a classic example. When you are traveling in a train and looking at the tree outside, the tree seems to be moving. And if you are looking at the tree from a bench beneath it, it is stationary. So before we specify the coordinates of this tree, we must specify from where we are looking at it. That is from train reference frame or bench reference frame. Now there are different categories in which frames can be classified, like stationary or non-moving frames. For example, ground frame is a stationary frame. Second, moving frames. For example, train frame is moving with respect to ground observer. Another type is inertial frames. When frame is moving with constant velocity and is not at all accelerated, then it is called as inertial frame. For example, if you are inside a vehicle which is going at a constant speed, then you are in an inertial frame. Lastly, non-inertial frames. When frame is in accelerated motion, such frames are called as non-inertial frames. For example, when you are in a vehicle which is just getting started or its speed is just getting changed, then that frame is a non-inertial frame. Note that frame being in motion and object you are looking at being in motion are two different things. Now, there is generally a confusion on what can be selected as a frame. Remember, everything is in every frame, meaning you can choose anything as your frame of reference and anything as your study object. And how to name a frame? The name of the object that is given to the frame must be at rest in that frame. Meaning, if I say my frame of reference is train, then that means for me train is stationary. Train might be moving for an observer in ground frame for whom ground is stationary. As discussed in the earlier example, whether the tree is in motion or not is decided by the frame of reference through which we are looking at it. Just like velocity of tree, some other physical quantities also change if we change the frame of reference. On this basis, physical quantities are classified into two categories. First, relative quantities, the quantities that change with change of reference frame. Second, absolute quantities, the quantities that do not change with change of reference frame. They are also called as invariant quantities. In essence, if we can just list down the relative and absolute quantities, that will make up the statement of principle of relativity. But how do we check theoretically whether the given quantity changes with change of reference frame or not? And if it changes, then how? For this, we need something called as transformation equations. These equations are required to calculate physical quantities in one frame if their values are already known in some other frame. In a way, transformation equations link the two frames. Thus, in technical terms, principle of relativity is a statement defining the invariant under given transformation equations. Newton first came up with relativity principle using Galilean transformation equations. So first we will explore that so as to see its limitations and thereby understanding the importance of Einstein's special relativity in a greater detail. Just a last note, Einstein's relativity is called special because it pertains to a special type of reference frame, that is inertial or unaccelerated frames. So we will be considering only inertial frames throughout this course.